Hi everyone, in today's video we're going to be talking about the angle of climb during the climb stage. So this also means that we have finished the takeoff section of the general performance theory, and now we begin the climb section of the general performance theory. Okay, so angle of climb is going to be basically the equivalent of the flight path angle in our discussion, which is going to be the angle between the local horizontal and the flight path of the aircraft. And so why do we need the angle of climb for? So for two main reasons. The first one being obstacle clearance calculations, about which we have already talked a little bit. And the second area that we need it for is climb gradient calculations. Okay, so the first one, obstacle clearance calculations, I think are very straightforward. Let's just sort of refresh it, however. So obstacle clearance, here we have a nice old plane. Here we have the screen height that we have achieved after takeoff, and here's the flight path of the aircraft. Okay, and generally speaking, we're gonna have some significant obstacles in our takeoff flight path. Usually this is how we sort of denote it. This can be a radio tower, mountain, any terrain. So basically any man-made or natural obstacle on the takeoff flight path. And of course this is the flight path along which the center of gravity of the aircraft travels along, as we have concluded several times. Okay, and we have also stated that the obstacle clearance is going to be the vertical distance between the highest point of the obstacle and the flight path angle. So this distance is the obstacle clearance. And we can define the flight path. We can calculate it or draw it, plot it basically, with the help of the flight path angle. And this is what we're also going to call the angle of climb in the Pad Pilot book. So this is what they're referring to when they're saying AOC, not Air Operator Certificate, which you can find it as a shortification in other subjects. So AOC is going to be angle of climb in performance books, generally speaking, especially in Pad Pilot. Okay, so here it's visible that if we know the flight path angle or the angle of climb, and if we know this distance from the screen height until we get to the point above the obstacle, so this x distance relative to the ground, I can calculate if I know the angle and if I know this side of the triangle. Because if you look at it, this whole problem, let's use another color to make it visible. So this whole problem can be modeled by basically a triangle at right angles, right? Where this would be the x distance that I traveled on the ground, and this can be a z vertical direction which I have climbed during this period where I covered the x ground distance on the ground. And if I know the gamma, I can fairly simply speaking easily calculate the z, right? Because I'm going to say that the tangent of this gamma flight path angle is going to be the z distance over the x ground, and from this one I can calculate the z, right? And if I know the z, so basically this distance right over here, the z distance, and if I add the screen height, I can basically calculate the difference between the obstacles height, OH, and the flight path, and that will be my obstacle clearance. Right, so, oh, sorry. So this is going to be a fairly common calculation that we'll do with the flight path angle. And this is just, roughly speaking, the theory which we'll use to calculate the obstacle clearance. Is not really mandatory to understand it now. This was sort of meant as an introduction to what we're going to do. But this is going to be sort of the aim of doing these kinds of calculations, the obstacle clearance calculations. Okay, so the second thing is the gradient calculation, the climb gradient calculation. So the climb gradient is, roughly speaking, the tangent of the flight path angle, and usually expressed as a percentage. So what do we mean by that? Let's say that we have, same old plane, nice little field with grass and everything, and we have the screen height, we have the local horizontal, and we have the flight path of the aircraft right here. And let's say I'm interested in finding out, like, what is the distance, the delta z that I cover. So what is the height which I gain over the distance which I cover on the ground. So this x, g, and d. You can see that it's so x, g, and d would be the horizontal distance that I cover on the ground, or relative to the ground, covered relative to the ground, and the delta z is the height gained. So let's say that I gained 5 meters of height while covering 100 meters on the ground. So in this case, we can see that the tangent, so and of course this one is the flight path angle, right? So, or the angle of climb in this case, because we're talking about a positive value. This case is going to be an angle of climb. So the tangent for the flight path angle, or the angle of climb, is going to be delta z over with x, g, and d, which is 5 meters over 100 meters, which is 0.05, right? And this is what we're going to say is the gradient. This is how I index it. I haven't really found like a very uniform indexation for gradient. So what we say is gradient in percentage is the tangent of the gamma times 100. Therefore, in this case, in this example, is 0.05 times 100. So therefore, 5%. So the gradient in this example, so if you cover 5 meters for every 100 meters, so vertically for every 100 meters you cover on the ground horizontally, then your gradient in percentage is 5%. Why is that interesting? Because usually speaking, this is more interesting in instrument flying. Because in instrument flying, we have something known as standard. So in air flying, we have what is known as standard instrument departures and standard terminal arrivals. And this is used for after takeoff. So basically on the climb section, the departure section after you've taken off from an airport, and the terminal arrival is before landing, is basically the arrival. So before you do the approach section. And I wanted to give you guys an example. Okay, so what I wanted to point is that here you have up in the upper right corner, it says that this is a Poprad Slovakia SID. So it's an SID, which means that it's a standard instrument departure. And usually they're going to give you a whole lot of routing. So here you can see the runway itself and different types of departures. So one is departing from one of the runways, so 27, and the other is departing from runway 09er, and you have different sort of departures, and these different sort of departures have different names. So for example, this one is called ATPL 4 Bravo, and this one is called ATPL 1 X-ray. Right, and it has different departure routings. So you usually go to a radio navigation station, you fly a DME arc of some sort, you join a radial, and so on and so forth. That's not exactly the point. What I wanted to show you guys is that there's usually a requirement with regards to the so-called climb gradient. So you can see that at this section of the chart, and you can see at the top that it says these SIDs, so standard instrument departures, require minimum climb gradient. And you can see that for the different routings, basically, so ATPL 4 Bravo, ATPL 4 Charlie, it tells you 371 foot per nautical mile, right? So you climb 371 foot vertically per nautical mile, which you cover horizontally, and it's showing you the required gradient right here. It's 6.1%, and the other one is also 6.1%, up to 4,500 feet and up to 6,000 feet. And the ATPL 4 Charlie, interesting, up to 6,000 feet, it has a 6.1 requirement, and after that, up to 8,000 feet, an 8% gradient requirement. So it means that at a higher basically altitude, you have a higher gradient requirement to remain in controlled airspace. And if you're unable to comply, in that case, you have to inform ATC. Right. So generally speaking, this is why it's very, very important for us to be able to calculate these climb gradients, because these are sort of the limitations that tell us whether we can fly a given instrument departure or we cannot fly an instrument departure. And we'll see a bit later that these things are very, very dynamic. So just like the, if you remember, the climb limited takeoff mass and the runway limited takeoff mass is not the same for a given amount of airplane from one day to the other. It's the same thing with these climb gradients. It's going to be very, very dynamic. And because pilots are, generally speaking, not math geniuses, for the better or worse, you can also see that they give you this sort of table right here, which gives you the ground speed in knots for 75, 100, 150, 200, so on and so forth. And it's giving you the requirements, the 304 foot per nautical mile. It shows you if you're going, let's say, with 100 knots, let's say you're going with 100 knots, and you want to comply with the ATPL 4 Bravo, it tells you that you need to climb 371 foot per nautical mile. And here you have the 371 foot per nautical mile. So therefore, the minimum rate of climb that you need to achieve is 618 feet per minute, right? It's basically a table which helps you to convert the ground speed into this minimum requirement gradient, basically. And so, yet again, you learn about these charts in instrument flying, and it's much later on, but I just wanted to show you that these calculations are very much required in everyday flying, and these are very dynamic values. So this is why you have to sort of do the calculations in advance, so that you understand what your airplane is capable of and whether you're able or not to follow, for example, such an instrument departure. Because of course, if you're not able, then the operator needs to ensure, if you want to operate to this airport, for example, needs to ensure that you have an instrument departure which the aircraft can comply, and the instrument departure meets the obstacle clearance requirements. Okay, so this is basically the reasons why we need to sort of talk about it, and let's actually start talking about it in that case. So just as a refresher, how did we calculate this angle of climb or flight path angle? So let's start from the steady state climb condition. So in the steady state climb condition, it was a fairly simple situation. So we had the local horizontal, we had the local vertical, which was by definition like perpendicular to the local horizontal. You have the in which the gravitational acceleration acts along. We have the flight path of the aircraft. We have the flight path of the aircraft, and along which the center of gravity, of course, travels along. So we have the center, well, let's put it a bit higher. So we have the center of gravity somewhere here, let's say. Center of gravity, and we can define the longitudinal axis of the aircraft and the vertical axis of the aircraft, and this is of course the vertical axis of the Earth, the local vertical. Okay, so we can also go ahead with drawing like an aircraft silhouette. This is going to be our nice little aircraft right here. And let's draw the forces which act upon it. Okay, so we're going to have definitely, yeah, before we do, we also have the undisturbed airflow velocity, where the undisturbed airflow velocity has like three components, x, z, and y components, and we just said that the velocity acts purely in the negative longitudinal direction, so like that. Okay, in that case we can say that the lift is going to act perpendicular to that at right angle, so lift is acting in this direction. Of course, if we have lift, we're also going to have drag acting on the aircraft. We're also going to have some thrust. We'll make it a bit longer, so we have thrust acting in the positive longitudinal direction, and we're also going to have the weight of the aircraft acting parallel with the local vertical direction. Okay, so if you guys remember, we broke down the weight into two components. Basically, we have one which acts parallel to the longitudinal axis, and we have one which acts parallel to the vertical axis of the aeroplane, so it's VZ. And if you remember, the flight path angle, of course, in this case the angle of climb, can be defined up here as well, and from this we can calculate the WX component, so the sine of the gamma is basically the opposing side, which is the Wx over the W, so therefore the Wx is equal to the sine of gamma times the weight. That's how we can calculate this one. And of course the vertical component can be calculated in the following way, with the cosine of gamma is the adjacent side over the hypotenuse over the weight, so therefore the Wz is equal the cosine of gamma times the weight. Alright, this is how we calculated this component right over here. And if we want to sum the forces in all directions, so we want to sum the forces, we're going to have like three components: the sum of forces in the x direction, sum of forces in y, and some forces in the z direction. And let's start with the sum of forces in the x. Right, so sum of forces in the x direction. In the longitudinal direction, we have in the positive direction acting thrust. In the negative one, we have the drag and the weight apparent drag. So the sine gamma times the weight. And since this one is a steady state condition, it means that the acceleration is 0. So therefore, all of the acceleration components are 0. And most importantly, all of them are 0. And so what we can see further is that the sum of the forces is equal to the mass times the acceleration vector. So therefore, the acceleration vector is the sum of the forces over with the mass, which we can further express as the sum of the forces in the x direction over the mass, sum of the forces in the z or y direction over the mass, and sum of the forces in the z direction over with mass. And these all have to be equal to 0. So therefore, because we never divide with 0, right, so the mass is not equal to 0 in any case. So the mass is not equal to 0. Therefore, we can see from this one is that we can only get this equation if the sum of the forces in the x direction is 0, and the sum of the forces in the y direction and the sum of the forces in the z direction are basically 0. So like this. Sum of the forces in the y direction is 0, and the sum of the forces in the z direction are 0. Okay, so yet again, we're going to say that this has to equal 0. So therefore, what we can see is, yet again, sine of gamma equal thrust minus drag over weight. This is one very important formula. Right, and actually we have already talked about calculating all the other ones. You guys know how to do it. We're not going to go into a whole lot of detail because we already have what we came from, because this is the important formula. So yet again, there it is. So sine of gamma is the thrust minus the drag over with the weight. Okay, so therefore, here we have basically the entire formula and how to calculate it for the climb. And we also have, we can also look at the basically factors that influence this flight path angle, this gamma over here, right? Because of course, if the angle is 0, the sine is going to be 0 as well. And as the angle is increasing, the sine is increasing. So therefore, we can see that there's a direct correlation in how this fraction changes that will indicate as to how this flight path angle is going to behave, basically. Okay, so we can immediately see like what happens if the thrust is equal to the drag. then the whole expression is going to be 0, and the sine of the angle, so if we express it further, what we can see is that gamma is going to be the arc sine of thrust minus drag over weight, right? So if this expression right here is 0, then the entire fraction is going to be 0, and arc sine of 0 is going to be 0 degrees, right? So 0 degrees of angle of climb means basically cruise conditions, and this is what we got initially as cruise conditions, so this whole thing basically checks out. Okay, so what do you guys think we want to achieve during a climb? A larger flight path angle or a shallower one? But I think with the introduction and how we've discussed what this whole calculation is required for and why angle of climb is interesting, I think it makes sense that a larger flight path angle or a larger angle of climb is going to be most beneficial for us, right? It's going to be most beneficial. Okay, so therefore we can basically define a speed where we can travel, where we can fly with the best angle of climb. And the best angle of climb is going to be the largest angle of climb that I can squeeze out of the airplane. And we'll see in just a second what it's going to be a function of. But we're going to have here the definition of the so-called Vx, and this is very important. And this Vx is going to be the so-called speed for best angle of climb. Okay, so we want to basically optimize this this angle of climb. So what we're gonna see, we're gonna assume for now that the mass is constant. So therefore, we can clearly see if the mass is constant, that the whole expression is going to be a function of the excess thrust, right? So I want to maximize this excess thrust. What we can see here is that it's going to be different for two cases because of this thrust curve. Because the thrust curve is going to look different for propeller-driven aircraft and is going to look different for jet-driven aircraft. And this is why we said in the very beginning that those diagrams, diagram curve shapes for the thrust curve and for the power available curve are very, very important to distinguish, because here we're going to make like two major differences. So we're going to talk about first the easier one, is that the Vx for jet aircraft. So Vx for jet aircraft. Okay, so let's plot the thrust and the drag for a jet aircraft. So here we have basically we can have calibrated speed, we can have true airspeed, it doesn't really matter for this kind of discussion. Let's have calibrated airspeed. And here we're going to have, I'm going to use the same kind of colors as Pet Pilot does. So for the thrust, I'm going to have a red color, and for the drag, I'm going to have a blue color. Okay, so for the jet, as you remember, the thrust curve is basically a constant. So it looks pretty much like this. And the drag curve is just simply a drag curve. It looks like a drag curve like we have discussed. Okay, so this is the drag curve. Of course, the area of interest for us is going to be between the stall speed Vs and this point where the two curves intersect. This is going to be known as the Vmax S and L. So this Vmax S and L is known in the Pet Pilot book as the maximum straight and level speed and level speed. Right? It's called maximum strain level because in strain level conditions you need to have thrust equal to the drag. So therefore, this is the maximum speed where that can occur. So therefore, you're looking at this area, this shaded area between the two, right? And what you have between this area at any given speed is, well, let's examine what we have, is what is known as a thrust from the top side minus at the lower side is the drag for this speed, right? If I looked at this speed right here, another V, I have the thrust at the highest point minus the drag, right? So this is the resultant which I get from these two. If you remember how we called this thrust minus drag is the so-called excess thrust. And you can find this excess thrust in the formula of the flight path angle. If you remember, thrust minus drag over weight on the upper part of the fraction, so right here. So therefore, if the weight is a constant, then this excess thrust is going to directly influence my flight path angle, because if the excess thrust is larger, then my flight path angle is larger, and if the excess thrust is smaller, then the flight path angle is going to be slower as well. So what I'm looking for basically on this diagram is the place where I can achieve the highest excess thrust. And I think it's pretty convenient in this case, so this is why the jet is such a great for these kind of discussions, is that you're going to have a point, because the thrust curve is a constant, then the biggest difference is going to occur when your drag is minimum. And that occurs in the so-called VMD, as you have already learned. So VMD is the velocity for the least amount of drag. And this is also where the largest excess thrust occurs for the jet aircraft, and therefore the largest flight path angle can be achieved. So therefore we defined the Vx as a speed for best angle of climb, and for the jet is gonna be the VMD. But this Vx is not a constant, and it's not going to be the same for the propeller aircraft, so this is why we call it a Vx, not, for example, VMD, VMP, or whatever. It's not a, so from this one, you don't remember that the Vx is always VMD, but what you remember is that the Vx for the jet, the speed for the best angle of climb for the jet, is equal to the VMD. And if my understanding is correct, on the Airbus they also call this, if you ever see the so-called green dot speed, the green dot speed is the VMD, right? And if you fly, basically, if you fly with this VMD speed, you're going to achieve the best flight path angle, right? The greatest one. So what happens if you start flying with a lower speed? Then you're going to be the left of this initial one, and therefore your excess thrust is going to be smaller, right? The green area is going to be smaller, so therefore your flight path angle is going to reduce if you fly at a lower speed than this VMD, right? But if you go back to the VMD, your flight path angle is going to go right back up, and you're going to achieve the largest flight path angle. What happens if you fly at a faster speed than the VMD? In that case, your excess thrust is going to still reduce because your drag is increasing. So if the excess thrust is reducing, the flight path angle is going to reduce, and the flight path angle is going to reduce all the same, right? In this case as well. So the flight path angle is largest is largest when flown at VMD for a jet. In any other scenario, the flight path angle is gonna be less. Okay, so let's see what the case is for the propeller-driven aircraft. It's gonna be a bit more difficult because it's not as exact as it is for the jet. Basically, so what we have right here, let's plot the so VX4 propeller-driven aircraft. So let's plot the same values. So we are going to have the thrust and drag curve of the propeller-driven aircraft in function of the calibrated airspeed. So let's use the red for the thrust and the same color, so the blue for the drag. So the drag curve looks pretty much the same. Let's start it a bit lower. There you have it. So there's your drag curve. And I'm trying to draw a very similar drawing to what you have in the Path Pilot book. So there you have it. So the thrust curve looks something like this. Okay. So yet again, we're gonna be looking at values above the V stall and below the Vmax SNL. Okay, so here we have approximately the VMD at the lowest point. So here you have the VMD, and this is the area, sorry, it's a bit thick. So approximately, like, this is the area which you can use for the excess thrust calculation. Okay, so generally speaking, this value is gonna be somewhere right here, and unfortunately there's no better way in explaining this one. Generally speaking, the reason you can see it is because the thrust curve of the propeller-driven aircraft is not so exact as it was for the jet-driven aircraft. However, a good way of remembering is that if you look at the VMD, generally speaking, the area to the left, you have the drag increasing. However, you have still, if you look at the image in the Path Pilot books, you still have a larger increase in the thrust than you have increase in the drag. So it's going to be definitely to the left of the VMD. But if you look after a certain while, around this area, so this might actually be even more to the left. If you look at the near the stall speed, so around like this region, you can see that at the very end of this curve, the drag is increasing quite steeply with only a smaller increase in the thrust. So therefore, it's going to definitely be to the right of this section. It's definitely not going to be higher than the VMD, because you can see that the thrust is basically decreasing and the drag is increasing after this. So it's definitely not going to be in this direction. So it's generally speaking is going to be lower than the VMD, and it's going to be closer to the so-called VMP, but it's not necessarily going to be exactly VMP, right? It's going to be dependent on the engine and propeller type and the altitude. So there's no like exact value to remember the VX from, but it's definitely, so for the propeller is slower than VMD. So therefore, we can generally say that the VX prop is also slower than the VX for the jet. Right, so the best angle of climb speed for the propeller-driven aircraft, and this is how you can sort of remember it. Okay. So this is just as a note. So in the EASA exams, VMD is considered to correspond with an angle of attack of 4 degrees, which means that a jet aircraft climbing at VX is climbing with a 4-degree angle of attack. And in case of the propeller-driven aircraft, the VX is slower than the VMD, so therefore you would consider the VX to be greater than the 4 degrees. This 4 degree, I don't know where it came from, is not an exact value. It doesn't correspond to any like given aeroplane. It's just a sort of given value, but if they ask you like what angle of attack is an aircraft having when it's cruising at VMD, the answer is in that case is 4 degrees. Okay.